Hello everybody, my name is Matthew Virden and I am with Mississippi State University Extension, and today I'm going to be talking about influence of boat wakes on wave climate in Back Bay, Mississippi. First, why do we need to know wave climates? Wave energy is an important driver in sediment transport, hydrodynamics, and erosion, and understanding these interactions can help identifying the causes of shoreline degradation. Also, understanding how wave climates will impact shoreline project areas can help inform how those shoreline projects are designed so that they can be prepared for the wave climates that they will experience. Current wave climate considerations typically use wave models to predict the waves that a specific area or bay might encounter. The wave models use wind data like that used to create the wind rows at the bottom of the screen to predict the waves that the specific area might encounter. However, current wave model predictors do not incorporate vessel-generated waves into their predictions. And knowing that this knowledge gap existed, we wanted to know exactly how vessel-generated waves influence wave climates in Back Bay. To get a better understanding of how vessel-generated waves influence the wave climate in Back Bay, Mississippi, we used our DIY wave gauges to get accurate wave data for the July 4th weekend of 2019. We deployed around 20 gauges, and the goal was to capture both maximum and minimum boat activity and compare the two. Wave gauges were deployed from Wednesday, July 3rd to Monday, July 8th at various locations in Back Bay. The goal was to have gauges in fetch limited or protected areas and areas that were unprotected where we typically see more wind generated waves. We also had the goal of placing gauges near boating channels where we would see peak boating activity, and also locations away from boating channels where we would see less boating activity. After gauge deployment, the data was brought back for analysis. The raw data was broken into 3 different time periods. The first was maximum boat activity, which was Thursday, July 4th from 7 to 10 p.m. The next was a low boat activity and a low wind period, which was Thursday night and Friday morning of July 4th and 5th from 11 p.m. to 2 a.m. And last was the high wind period, which was Sunday, July 7th from 3 to 6 p.m. Those time periods were then sent through the MATLAB analysis code like that on the bottom left to get the wave heights during that time period. For each time period, we wanted to look at the number of waves that occurred at specific wave heights, and those wave heights were 4 to 7 centimeters, 7 to 10 centimeters, and 10 plus centimeters. The reason we wanted to look at the number of waves at specific wave heights instead of a statistic like significant wave height is because we wanted to focus in on those larger waves which we expect to be vessel driven, and sometimes those waves can be drowned out in statistics like significant wave height due to the vast number of waves that are from 1 to 3 centimeters throwing off the number. Wind activity was also captured for all the time periods, and they're displayed here in arrows. During the maximum boating activity, the wind was generally out of the southwest and ranged from 0.1 to 2.7 miles per hour. During the low boating activity / low wind period, which was July 4th and 5th from 11 to 2 a.m., the wind speed was very light at 0.1 mile per hour, and sometimes it was coming out of the west and sometimes out of the southeast, so we have 2 arrows for this time period. During the high wind period, which was July 7th from 3 to 6 p.m., the wind speed ranged from 2.7 to 5.8 miles per hour and came out of the southwest. So now I want to focus in on 2 separate pairs of wave gauges to see what wave heights we recorded at those gauge locations. So first I'm going to start here on the east side of Back Bay, and I have 2 gauges, gauge A and gauge B. Gauge A is one of those unprotected sites where we were expecting to see more wind generated waves, and gauge B is one of the protected sites and also adjacent to a boating channel where we were hoping to capture more of the vessel generated waves and be protected from the wind generated waves. First, I want to look at the maximum boating activity time period for these 2 gauges. We did see an increase in the 7 to 10 centimeter category and 10 plus centimeter category when comparing our protected site to our unprotected site, which is what we'd expect since our protected site is adjacent to a boating channel. However, our unprotected site did have a larger number of 4 to 7 centimeter waves, and we believe that the majority of those waves are wind generated due to the wind coming out of the southwest. Our protected site, 4 to 7 centimeter waves, we believe the majority are vessel driven due to the adjacent boating channel. Next, I want to look at the low boat activity / low wind period. And a reminder, the wind was 0.1 miles per hour, 1 hour out of the west and another hour out of the southeast. So we're expecting very few or none wind generated waves during this time period. And as you can see on gauge A, we saw 0 for all different wave height categories, which is what we expected. For gauge B, we did see a small number of waves in all 3 categories, and we believe this to be caused by a vessel coming through in the middle of the night right by that gauge, since it is adjacent to a boating channel. Next, I want to look at the high wind period for these 2 gauges, and we saw exactly what we expected. For our unprotected site, we saw an increase in waves due to the wind generated waves from the southwest, and for our protected site, we saw a decrease in waves because that site was protected from these winds, except for our 10 plus centimeter waves, which we did see a small increase when compared to our unprotected. We believe that this is caused by a vessel traveling through the boat channel. Now I want to compare 2 time periods of high boating activity and high wind activity for these 2 gauges. If you look at gauge A at our unprotected site, we see what we expected. As the wind speed increased from our high boating activity to our high wind activity, we saw a larger number of waves at your 4 to 7, your 7 to 10 centimeter wave categories, which is what we'd expect. However, it was opposite when you looked at your protected site for those 2 time periods. We saw an increase when we went from our high wind period to our high boating period. We believe that this is caused by boating activity along that boating channel. And it's important to note, if you look at the 7 to 10 centimeter and the 10 plus centimeter categories, the highest values were located at the protected site during that high boating activity time period. So they're even larger than the unprotected site during the high wind activity time period, when we typically expect the largest number of waves. Next, we're going to move over to the west side of Back Bay to look at 2 more gauges and see how they compare to each other and how they compare to the 2 gauges we looked at before. So once again, we have 2 gauges. Gauge A is at that unprotected site where we're expecting to capture more wind generated waves, and gauge B is in that protected site next and adjacent to a boating channel where we were expecting to get less wind generated waves and more vessel generated waves. So first I want to look at the maximum boating activity for these 2 gauges, and once again the wind was out of the southwest, 0.1 to 2.7 miles per hour. And similar to the 2 gauges we saw before, at our unprotected site gauge A we saw a small number of 4 to 7 centimeter waves, and then we've looked at gauge B, we saw an increase, higher numbers in every single category when compared to gauge A, and we expect this to be caused by a vessel traveling on those boating channels causing a large number of waves. Next, I want to look at the low boat activity and low wind period for these 2 gauges. As we expected, we did see a small number in all wave categories at both these locations. We believe that the numbers that we did see are caused by late night vessels traveling along the boating channels causing these waves. Next, I want to look at the high wind period for these 2 gauges. And we do see an increase from our unprotected site to our protected site for both the 4 to 7 centimeter waves and the 7 to 10 centimeter waves. We believe this to be caused by vessels traveling along that boat channel during this time period. Once again, I want to compare the 2 time periods of high boating activity and high wind activity for these 2 gauges, and this comparison was very similar to the comparison of the other 2 gauges. We saw an increase when comparing at our unprotected site from our high boating activity to our high wind activity for the 4 to 7 centimeter wave slot, which is what we'd expect with an increase in wind speed. At our protected site B, we did see increases and decreases when comparing the 2 time periods, which is what we might expect because vessels were present during both those time periods. But we did see a larger number at our 10 plus centimeter waves for the high boating activity, which is what we'd expect with the increase in vessel generated waves. Most important, if you look at our protected site B At the high boat activity time period, we saw an increase in almost every category when compared to our unprotected site at the high wind activity. So at our vessels are generating larger and more frequent waves at our protected site when compared to the unprotected site with wind generated waves. So what does this mean? This means that protected areas are experiencing intense vessel-generated waves that could be comparable to wind-generated waves, and unprotected or exposed sites. And we know that there's a linear relationship between wave power and erosion, so these protected sites might not be adapted to the intense vessel-generated waves that are occurring in that area. And if there is a shoreline project located in these protected areas and are not designed to withstand that wave climate, they will potentially fail. So the next steps to get a better understanding of what exactly is going on here, we need to incorporate the wave power equation, which is this equation here. And from this equation, we know that wave heights have an exponential relationship with wave power. So this means that those larger intense vessel generated waves have the potential to generate more wave power than the typically smaller wind generated waves, but we want to know exactly what they are adding to the cumulative wave power that an area might experience. So we're going to use the wave power equation to expand the table we had before. That way we can get cumulative wave power for each of those segments of wave heights. That way we can understand how those wave heights are contributing to the overall wave climate of those areas. Thank you for listening to my recorded presentation. Thank you to MAPHIS for funding, and Margaret A. Davidson Fellowship for future funding, and Mississippi DMR for permitting.